anybody will watch it, but I'll record it and post it to the internet. Uh, if we think of maybe, let's think of some things in your everyday life that are examples of this. So I don't know how you guys travel, but and Jenna, you and I have talked about this. Every day before I leave from my house, I open up my phone and I first click on Google Maps, and then I have my work address saved in there. And then it gives me like 3 or 4 options on how I can get here. And I look at that and I say, okay, which way am I going to take today? Similarly, then I might open that other app, Waze. I don't know if you're familiar with that one. And I look to see which Waze, what is Waze telling me? What is its algorithm suggesting that I do? You know, if it's certain times of the day, a route for me is quicker than other routes, depending on traffic and all that. And so what I'm doing is I'm taking advantage of something that Google Maps does and that Waze does, is they are optimizing something. They are giving you options. I want to know what is the quickest route that I can get from point A to point B. Now, when you're young and when you're a little kid in math class, they usually say, well, the quickest way to get from point A to point B is a straight line, right? But we know that's not necessarily the truth in the real world, right? Does a plane fly from New York City to Shanghai, China in a straight line? No. It flies over some curved, what we call an arc or a trajectory. So when I'm driving to work, I'm not going in a straight line. How quickly I get to work depends on what roads I take, what are the speed limits, what is the traffic density. There's all kinds of different things that affect how long it's going to take me to get here. Does that make sense? So in one way, what Google is doing when it suggests routes is it is optimizing in the sense that it is telling me what are the quickest ways for me to get to work. There's probably a gazillion ways I can drive from my house to here. There's probably infinitely many if you think about it, right? But what Google's doing is it's finding, usually what it does is it suggests the 3 fastest. And it'll usually suggest them in a situation where one might be toll or non-toll. So it's giving you suggestions and things it might think that you are interested in. Another scenario that you might be familiar with is, okay, suppose we run a business. What is likely the number one goal of someone running a business? Their job is to maximize their profits. Now, how do you maximize profits? How do you make the most money? You make the most money by minimizing or spending the least amount of money, but finding out how to get your maximum revenue. So your profit is all the money you bring in minus what it costs you to produce and distribute. Very simple, right? Like if you make a lemonade stand, the only money you profit is how much money you charge for your lemonade and how many you sell a bunch, you add all up how much how many you sold times how much each one costs, but then you have to subtract all your things that you bought in order to make that lemonade. So once again, we see this idea of our goal is to maximize something or minimize something. If I produce a product that I want to ship, I'm Amazon, for example. I guess they don't necessarily always produce, but Amazon's job when they take your order is to figure out, okay, well, how do I ship it? Think about all the quote unquote optimizing that's happening there. First, what kind of box do I put it in? If I'm sending a cell phone, do I need to put it in a box this big? I guess I could, but is that cost efficient? Is that efficient as far as packing as many as I can into a truck or a plane? Then the next thing, once you box it and you get it on a truck, how do they decide? I mean, you ever think about who decides which route the mailman's going to take or the mailwoman or the UPS driver's going to take? You think they just load up a truck in the morning and say, okay, now just drive around and see what happens? That's not what happens, right? The idea is that there is a science behind it. And more importantly, how efficient can we get these things to where they need to go? So these are real world problems. There's a great story about this recently, and I like to share this. So if you're bored by it, it's okay, but I'm going to share it with you anyhow. If I'm going to go to the internet for a second, and I'll actually go to Google Maps. So I found it funny 2 years ago, we're on an airplane. I was flying from Pittsburgh to Chicago. And then on the way home, we came obviously from Chicago to Pittsburgh. And I was talking and I heard, not talking, but there was a mother with her young kid. And if you've ever been on an airplane in the last few years, a lot of airplanes now have monitors in the seat in front of you. You can watch TV. Some of them even allow you to look at your flight path and your height and all the statistics. And what we found to be interesting is that we literally, well, I didn't find it to be interesting because I'm familiar with this, but the kid was dumbfounded because we flew out of Chicago and then we went up through Michigan, in through Canada, and then we came down like this. That's how we flew into Pittsburgh. Whereas to the child would have thought, well, if I'm flying from Chicago to Pittsburgh, let me just do this. And the intuition is it's a shorter distance. But the fact of the matter is we don't know the conditions in that trajectory. Perhaps the winds are stronger down here than they are up here. Perhaps there's different weather patterns. Perhaps there's different pressure. And so it just so happens, even though we took a longer path, we actually landed in Pittsburgh quicker than we would have had we flown straight for whatever reason. I guess quicker is a bad way. It was more efficient because if you, I guess the better way to say it is if you incorporate fuel consumed and time, right? This happy medium. And maybe you've heard of things like the jet stream and how winds move. Typically, when you fly east to west and across the United States, it's longer than if you fly west to east because you're coming with the wind. So anyhow, these are real world problems, and the question is, how do you solve them? And so what we want to do today is introduce you to very simple baby versions of these watered down textbook type problems that are the same theme as this. Given a problem and a set of conditions, how do we optimize our solution? So again, given a problem, and typically our problem comes with certain conditions. And so these kind of problems, they have a broad name. They're called optimization problems. And really, you guys may be actually familiar with some very simple ones of these from perhaps an algebra class in high school or middle school. They likely didn't call them this, but that's what they are. And by the way, these are, unfortunately for many of you, it's a nightmare because these are what we call the story problems or the applications, or what did we call them when I was a kid? Word problems. Everybody hated word problems, right? Oh my God. Yeah, because the word problems, they require more of you. It's not just that you know the math. Knowing the math's not enough in a word problem. In a word problem, you have to be able to translate English to math and vice versa. And then you have to know the math, at least the appropriate math to solve the problem. So anyhow, that's what we want to talk about today, and hopefully you will enjoy it. And I have to get my thing. Excuse me. I hit the wrong. Once again, I do the same stupid thing. So, any questions before we do this? All right. So we'll start with sort of a very basic scenario. So imagine you want to enclose your yard. Let's assume you have a yard with a fence. And let's make it fun. You want to enclose your yard with a fence, so your pet giraffe. Let's make it giraffe. Does giraffe have one E or two E's? Let's Google that. I don't know. You know the nice thing about it is two E's. The best thing about the modern world, if you don't know how to spell something, I literally just put it into my phone, and my phone tells me it's two F's. See, there you go. Modern technology. So your pet giraffe can play safely, right? No tigers coming to eat your giraffe. All right, so let's imagine a sort of pseudo real world situation. Let's imagine we have a budget, so we only have so much money to build our fence. Right? And let's imagine that we can't get too creative. How are we going to fence in our yard? Let's probably do the simplest way possible. Let's fence in a rectangle. And then we can do what most people do when they fence in their backyard for pets. Is one side of the rectangle is not a fence. It's usually the house. Does that make any sense? So your budget allows you to purchase, let's say, 250 feet. Well, let's say 250 yards, because we got a giraffe. You got to give him space. You're rich. You have a big yard. Your budget allows you to purchase 250 yards of fence. So this is one important thing we're going to do. The next important thing we're going to do is we're going to say, for simplicity, we will construct a rectangular fence. And then lastly, we will use we will use the house as one side of the fence. So to see what we mean by that, we're going to draw a picture. So we'll say as shown in our picture. How about we say our blueprints? That's more fun. That's like the fancy words. Okay, so this is the information we're given. Again, this is a watered down real world scenario, but it is in fact a scenario you can imagine. So here's the question. What dimensions should we choose to maximize our enclosed area? I mean, we want to give our giraffe as much space as possible. So let's look at what this picture could be. I'm going to look at the overhead. I have my little satellite Google Maps image of my house. So let's get out a rectangle. We'll put this creature right here. Here's our house. And we need another rectangle, but we'll do it differently. So here's our house. And this is from above. And then we have our fence, which we'll do purple. Now, I'm not going to draw a rectangle because remember, what I'm assuming is that here's my enclosed area. And what I need to do is I'm trying to determine how I should build this. So let's note that these guys have to have some sort of value, right? So again, this is my fence. I only need 3 sides of my fence. Why do I only need 3 sides? Because one side of the fence is going to be the house. Now again, it's a silly concocted problem, but nonetheless, the theme is what's important. How do I obtain the maximum area? Now look, you might say, well, what do you mean maximum area? It's not going to matter. Yeah, it is. Depending on what number you choose for y and x, it's going to have a different area. So here's what we know from the given parts of the problem. What we know is this. Given our picture, if we look over here, what does number one? Our number one thing, by the way, we call these constraints. The fancy word for these things are constraints. If you reading the book or online. And so what we know from our first constraint is we only have so much fence. And that tells us that x plus 2y has to be 250 because that's how much fence I have. And you would think we want to use as much fence as we can buy. Now we also know the area of the enclosed is x times y. That's the area of a rectangle. So these two facts right here, we can deduce these from these 3 restrictions of our problem. So what's interesting is we have 2 equations, but we have 3 variables. And a better way of saying that is I have 3 unknowns. I have 3 unknowns. My unknown is x and y. How far should I make the fence go up and down? And how far should I make the fence go left and right? Those are unknowns. And then also, once I figure those out, they will give me the area. So right now I have 2 equations and I have 3 unknowns. And the good news is those 3 unknowns are related in a very specific way. You could see it right here. So the word maximize here is very, very important. It's very operative. It's telling us what we want to do. And so that means that we should somehow think, well, we need to analyze the area because our job is to make it as big as possible. And if we think about what we've been doing the last few classes, well, we understand that in order to maximize something, we need to do what? We need to analyze the function's derivative. But the issue right here is I don't have a function. I have two equations. So what we need to understand is the following. We need a function for A. That's what we need. If we want to be able to use calculus, we need a function for A. If we want to maximize area, we need to have a function that tells us the area so that we can take its derivative, find the critical numbers, and use one of our derivative tests to determine a max or min. That's what we need. So to do this, how do we get this? Well, so we can solve the equation 1. We can solve that for y. So what if I solve that for y, I get 250 minus x over 2. And then sub this in. I guess we'll say into 2. So if I sub this into 2, I get area is x times y, length times width. Or area equals, in terms of x, is x times 250 minus x over 2, which we can rewrite as 250 over 2 is 125. So we get 125x minus 1/2 x squared. So this usually takes a little bit for us to pick up on. So what is the area function? The area function is the area given a width of x is 125x minus 1/2 x squared. So it's important that you ask a question if you're not sure what's happening, because this is what you're going to do in every one of these problems. You're going to take the given constraints, you're going to manipulate them algebraically to obtain a function. And if you're confused by what I did here, this is nothing more than the distributive law. I need some Coke juice. Yes.
Is there a reason why for one you chose solve for y?
Does not matter. No, I could have. So the question for those of you at home, the question was, why did I solve for y here instead of x? It doesn't matter. I could have solved for x. It's just traditionally I liked, it's more convention than anything. In fact, it might have even been a little simpler to solve for x because then you wouldn't have the fraction. Do you understand what I mean? But it doesn't matter. I could have done it the other way. I just wanted my function to have x as a variable just because we're used to that. But you're right, it doesn't matter. And there's nothing, I could have used L and W instead of X and Y. You could use any letters you want. You could use cat and dog. But yeah, does that make sense? Okay, now, here's the thing. If we think about when this function makes sense, we understand that this is not the problem in general that we've been studying the last couple classes. Now, analyzing this function, we are restricted to a domain that makes sense. Like if this represents area, it doesn't make any sense if x is a negative number, right? It doesn't make sense if x is bigger than 250. Hell, if x was 249, it wouldn't really, that'd be a really weird rectangle. 240 by a half and a half. Think about that, right? But nonetheless, we can technically say that this function makes sense when x goes from 0 all the way up to 250. So this is important. The domain is x between 250 and 0. Since x is a length. Now, if I go back to this, some of you might be wise and say, well, Grady, all right, I already know this is a quadratic. And I know that its maximum occurs at the vertex, blah, blah, blah. And you could get that real easy. That's okay. That's fine. If you want to do that shortcut on this particular problem, that's fine. However, in general, that doesn't work. Because if this is a cubic or any function, sines and cosines, you don't get to rely on a very basic fact. You're going to have to reason what the max or min is. Do we understand that? So even though in some cases you can take advantage of things you learned and like real quick ideas like a parabola. Again, I hope you understand what I mean. This is an upside down parabola. It's not hard to figure out where its maximum is. You can probably do it in your head. But in general, you're going to have to take a derivative, find critical numbers, and then reason if it's a max or min. There are problems I can give you where it's not easy. Okay, so let's go through that even though we don't necessarily have to here. All right, so let me put it this way. This means we want the maximum of A on this interval. Now, here's an interesting thing to note that's obvious. If you replace x with 0, it's 0. So we know that ain't going to matter. And the same thing with 250. So we're not going to have to worry about it. So note, the derivative of A is 125 minus x. Right, that's a pretty simple derivative. 125, the 2's cancel, so you're minus x. So x equals 125 is the only critical number. Look at this other piece of reasoning I'm going to use. Since a prime of x is -1, and that's negative, the second derivative test says a of x has a max at x equals 125 yards. Now, all I've said right now is that this is a max. Technically, it's a low. It's only, all we know for sure is that it's a local max. We don't know that it's the global max, but that's not going to be hard to see. Before we do that, though, does anybody have a question, about this? Comments, concerns? So remember, if we restrict our variable, if we restrict our domain, we know we have an absolute max and an absolute min, and we're trying to find the global one. So the only thing we have to do now is check the endpoints. So that's what remains left. And this is going to be easy to see just by plugging some numbers in. So since a of 0 is 0, a of 250, well, these are the endpoints that I'm plugging in. What is a of 250? Well, it's 125 times 250 minus 1/2 times 250 squared. Now, you don't even have to, look, I guess you could, if you wanted to, you could compute this whole thing. But you can reason it a little quicker without actually doing that. Here's how you can do that. If I factor out a 250, I'm left with 125 minus 1/2 times 250. And of course, this also equals 0. So let me perhaps write it a little cleaner. So since a of 0 is 0, since a evaluated at 250 is equal to 0, and a evaluated at 125, which is our critical number, we know that that's at least a local max, but we can easily calculate that this is 125 squared minus 1/2 times 125 squared. So again, I'm using this function. And what does that equal? Well, that equals, you can multiply this out if you want, but this is just 1/2 times 125 squared. I don't know that number in my head. Maybe you do. So I'll go square 125 and then I'll divide it by 2. And when I do that, I get 15625 over 2, which is equal to 7812.5. So what do we conclude from this? We conclude the optimal dimensions are x equals 125. Now, if x equals 125, what does y have to be? Well, then you got to go back to this constraint where x plus 2y. So if you go to this thing, you get 250 minus 125 over 2 is 250 minus 125, which is 125, right? So you get 125 over 2. What's that? Is that what it is? We'll just leave it like that, though. But yeah, you're fine. You're correct. So there's a lot happening here, but you know, the purpose of the question asked to give the dimensions, I gave you the dimensions. And I know that they're absolutely correct because I applied the theory properly. This is an example, but before I say that, actually, does anybody have a comment, question? So a problem like this is an example of a more general problem that's actually quite important in many applications. They're called isoparametric problems. Yeah. And so the general problem states if you have some region and the question becomes given a fixed parameter or perimeter, what is the optimal area I can enclose? Now, the thing is we usually have restrictions, just like we talked about distance. So a good way to think about these kinds of these problems is imagine a cylinder. This is a cool problem. Imagine I have a point, 2 points on my cylinder. Perhaps even there's a point here and here. Is it always necessarily that the best path between the 2 points is straight down? Well, no, just like when we're talking about flying or something else, it might be the best path is to helix down around the cylinder to get from point A to point B, depending on the constraints we have. So these are problems that are studied. The mathematics is much more advanced, but again, these are the baby steps, or the baby problems, the fundamental ones that if you ever wanted to solve the more realistic stuff, you have to be able to start with these things. Any comments or questions about this? All right. So that's an example of a problem. Let's do another one. All right. So we want to build a box. Who knows? Maybe we're going to store our favorite CDs. Does anybody even own CDs? I have tons of them. They're just sitting in boxes. We want to build a box. The cost of the top and bottom are, let's say, $10 per square foot. the cost of the sides is, let's say, $5 per square foot. We want the length of the box to be 4 times the width. And its volume must be, let's say, 50 square or cubed feet. How can we minimize our cost? So sometimes we'll do problems like this. Someone will say, well, why does the sides have a different cost? I don't know. Maybe they need thicker top and bottom, so it's more expensive. I don't know. It's a problem. It's a toy problem. If you think this is stupid, okay, then go minimize, go ahead and go solve the Amazon problem of minimizing cost shipping products. I don't know. I don't know what the hell you want to do. It's a toy problem. It's a baby problem. You got to start with baby problems. All right. How can we minimize costs? So we're going to move a little quicker in this problem, but of course you have your notes to come back and please ask if you can. So the first thing you need to do is you got to draw a picture. So I'm going to draw my box. Here's my box. Now, I like to think of boxes 2 ways. First, I like to draw my 3-dimensional box. That's what my box looks like. It clearly ain't to scale, but let's say, okay, I'm reloaded. Ooh. Here's like a box, right? I'm trying to give it some perspective. And what do we know about this box? It has dimensions. It has, let's call this a height. We'll call this a width. And we'll call this the length. Now, what we know about the length, though, is the length is what? We had a 4 times the width. So we know that the length is 4 times W. We know that. Now, sometimes I think it's useful to take scissors, fake scissors, or as my kids say, for pretend. And I like to cut down these seams. So I'm going to cut down here, I'm going to cut here, 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 and I'm going to lay my box out. Lay it flat on the floor. So if I lay my box flat on the floor, what does it look like? Well, I have my base. My base is 4W. W, and this, again, I'll write this is the base. I'll explain why I'm going to do this in a second. And then I have my sides. So let me get, here I have a side. Here I have a side. Here I have a side, and then here I have a side. Now, what are the dimensions here? Well, this is H, etc. Of course, this is still W. And then this guy is 4W. And then don't forget, a box is made up of 6 things, right? It has a top, a bottom, and 4 sides. So let's label these so we understand. We'll call this side 1, side 2, side 3. I'll call this side 4. And then don't forget the top. So I'll come up here and I'll draw the top. Move this out of the way. The top has the same exact dimensions as the bottom. So I'll draw it separately just to. So this would be 4W and then by W. So this is the top. Now, actually, you know what I should do? I should color code these based on, let's do that. I'll color code them based on their dimensions. Make it a little easier for the peeps. Does anybody have a comment, question, curiosity? I'm not saying you have to think of it this way. This is what I like to do. So at first I have my box, and then I decide I'm going to cut it down the seams, and I'm going to lay it flat. I like to visualize it both ways like this, because on the left-hand side, when I'm trying to draw it in 3D, I can think of it in terms of its volume, length times width times height, LWH. But on the right-hand side, when I lay it flat, it's a lot easier to visualize the surface area. How much material do I need to construct it? Again, this is just my opinion. Maybe someone else has a better way of teaching this. I don't know. But here's what we get. So I'm going to look at the left-hand side. The left-hand side, I have this volume thing. So let's draw that, and we need a color. We'll use this weird maroonish brown. The volume here, volume is length times width times height. So let me actually draw it over here because we're going to write it 2 ways. So the volume is length, width, height, or if you'd like, knowing what we know about this problem, what can we say? Well, we can say that we need the volume, it has to be 50, right? And then we know that length is 4W. So instead of writing that, what I'm going to write is I'm going to write 4W squared times height. And we'll put like a little pretty little red little cloud around this creature because it's so cute. And then over here, I need another color. How about we use this dark ass green? I don't know. A lot of issues. I think see what happens. I start drinking this caffeine and it's on. It's on. Check my, oh my God, I have messages. Oh my God. How do my friends work? They just sit and text all day. But they all have money. Like, it's what I'm saying. Like, that's what you need. You need a job where you very little work. So they're complaining about these elections. Not complaining, they're discussing. All right, now, what are we trying to minimize? Well, we're trying to minimize cost, the materials that we're using to build this. So we need to think about what we're told. So if we go to the previous page, we know the top and bottom cost $10 a square foot. So this is $10. By the way, if you're one of these people that do this, like if you're one of these people that do this, get out of my life. I despise this. This is not correct. The damn $ goes in front. It makes me think, and I shouldn't say this, it makes me feel like people, I understand that it's not the same everywhere. Right, and then I know the sides are all, what did I say, $6? 5, okay, that's good, 5, that's cute. $5, so this is $5, This is $5 a square foot, 5 pesos a square foot, 5 pesos a square foot. So what is our cost? Well, I'm going to use the letter C for that, and I'm going to write it in. I need a color here. We'll use red. So our cost is the following. Let's do the top and bottom first. So it's $10 times 2 of them, right? So it's 10 times what's, instead of length and width, it's going to be 10 times 4w squared. Plus, now, my sides are $5. How many sides do I have? Well, I have 4 sides, but 2 are different dimensions than the other. So if I do side 1 and side 2, the dimensions here are 4w by h. So I have 2 of these. So that would be 8wh. Provided we didn't make an error. So let me actually go a little slower. I don't want to get too far ahead of myself. So if I look at the top is 4w times w. So its area is 4w squared, right? So really, I should have, what should I have here? I shouldn't have, maybe I should write this. Well, I don't want to put it on the next page. So this should not be just, let me go clear. So they're $10 a pop. And then I have 2, count them 2 times 4w squared. Because there's 2 of them. So maybe that'll make it a little easier to see this. Now the next ones are $5 a piece. And then how many do I have of side 1 and side 3? I have 2 of them. And what are their dimensions? Their dimensions are 4wh. And then I also have 2 of side, side 2 and side 4, and those are wh. So that's 2wh. Yikes. So I'd like to try to clean this up. I'm running out of space, but just for the sake of it, it's 80w squared. So I don't know why I wrote this h like this. That was not, it's just not a power. Yeah, I don't know what the heck that was. It's me trying to look and write simultaneously. And so what you have here is you have 8 and 2 is 10. So if I do my math correctly, you get 50 wh. Or am I doing that wrong? 2 and 4 is 8. 8 and is, no. 8 and 2 is 10. 10 times 5 is 50, but I feel like that. Am I losing my mind? Did I do arithmetic incorrect? Say that again. So let's just double check again. This side, so side 4, the area is WH, and there's 2 of them. So yeah, that's where this 2WH comes from. Side 1 and 3, the area is H times 4W. So that's where I got the 4WH, but there's 2 of those guys. So then 2 and 4 is 8, 8 and 2 is 10, so 50WH, provided we did not make an error. Okay, so here's the problem. Just like we had in the previous example, our cost is dependent on two things. And we need to figure out how to eliminate one of those things if we want to be able to solve the problem. So just like in the previous problem, here's what happens. You have this constraint. You know you need a specific volume. So you can use that by plugging it into our cost function or our cost expression. And that allows us to obtain a function. So we have to decide, how do we want to solve it? And so like you suggested on the last one, I can solve this 50 equals, I can solve it for H or I can solve it for W. Now, being that W squared, in my opinion, I would rather solve for H because then I don't have a square root. So here's how I would go about doing this. So here's my reasoning, how I'm going to proceed. We need a function for C. So to get one, I'm going to solve 50 equals 4 W squared H for H. And when I do that, 50 over 4, well, is the same as 25 over 2. So I get H equals 25 over 2 W squared. So the first thing I'm going to do is I'm going to take and solve for H. Next, I'm going to sub this into my expression for C. So what was my expression for C? My expression for C from the previous page was 80W squared plus 50WH. So I'm going to plug that in. And when we simplify, you get 125 over 2W. Yikes. So we have a cost function. Where we have a function that gives us the cost when you give it a specific width. Which one? Right here? Yeah, should it be? That's a good point. It could be. Yes, it should be. That's my mistake. Well, that changes things, right? That should be 50. That should be 50. So what we end up getting is what? 25 squared, which is 625 over W. Good. Way to go. So 50 over 2 is 25. So I get 25 squared, right? Over W. Is this correct? I think that is correct. Yeah. So, and then again, what's 25 squared? 25 squared is the same as 20 plus 5 times 20 plus 5 squared. 625. I better check. Yeah. You can't get these things wrong. Gotta do them right. So this simplifies my mistake to 625 over W. And then of course, here we go. So all that's left then is to figure out what is the minimum value of this function. Whew. These are time consuming. We really, all right. So by the way, before we finish this, it's worth me reminding you, like I always do, that it's not easy to learn these things. It takes most humans quite some time to have a solid understanding of these examples. It's not going to make sense to you in 20 minutes or a half hour. So I'm not saying that for any other reason other than when you're stuck and you can't do it, that's normal. Most people don't know how to do these the first couple of days they try to do them. It takes practice. Okay, so we need to minimize this. So let's determine the absolute min on what are we using here? Well, are we restricted here? What is our what are we restricted to? How do we know? Obviously, the width, it doesn't make sense if our width is 0 or lower than 0, right? Negative width doesn't make sense. Also, our width can't be any bigger than 50 because we're saying the maximum, or we're saying that the volume has to be 50, correct? So we can determine the absolute min on the interval 0 to 50. So C prime of W is what? 160W minus 625 over W squared. So when does this equal 0? This equals 0 when 160W is equal to 625 over W squared, right? If I take it to the other side, and then I can multiply both sides by W squared, divide by 160. This is the same as W cubed equals 625 divided by 160. Now I don't know how to do that in my head, but a calculator tells me that 625 over 160 is the same as 125 over 32. Thus, the W we're looking for is the cubed root of this. Which we can clean up a little bit. What's the cubed root of 125? Well, that's 5, right? And then what's the cubed root of 32? I don't know for sure, but I do know that 32 is 8 times 4. And the cubed root of 8 is 2. So I can write this as 2 cube roots of 4, I guess, right? If I wanted to. So I can leave it like that, or we can just find what the approximation is. 1.575. So this guy, or the -1, but that makes no sense in context, right? Can we have a negative width? No, so we ignore it. And this guy is the only critical number. Well, I guess we could. Yeah, negative width. That'll. Oh my God, Biden just sent me a text. They need money to fight the lawyers. I was wondering because I was still getting texts and emails on Tuesday. I'm like, what do you need the money for now? All the commercials are done, but now they need money. Oh my God, it's 1:47. We got to leave. I apologize. Let's just finish this up. You should verify it's an absolute. This is the absolute min. All right, anyhow, have a good one. I'll see you tomorrow. Sorry, I didn't realize I was keeping you late. I should have known when you guys start packing up. I don't blame you, though. All right, guys, thank you very much. Take care, and hopefully I'll see you tomorrow. Hopefully. All right. Stay out of trouble.